Did you know the ground beneath your feet is like a giant mystery box, layered, churning, and full of secrets we've only begun to unravel? Imagine tunneling straight down through those rocks, through layers that get hotter, denser, and stranger until you reach a core so extreme it's beyond anything we can touch. How do we know what's really inside our planet? And how can we possibly know when no one has ever journeyed past the crust? Welcome to Physical Geology 001A at West Valley College. I'm Professor Farida Bucks Musa, and today we're going to uncover the hidden forces driving Earth's interior, the foundation for earthquakes, volcanoes, and plate tectonics. So let's get started. So first, where do our clues come from? Surprisingly, some arrive from outer space. Meteorites can be stony, packed with silicate minerals like peridotite, just like Earth's mantle. Others are nearly pure iron and nickel, resembling our planet's metallic core. And occasionally deep mantle rocks make rare appearances at the surface, tossed up by powerful tectonic forces. These fragments from space and from within offer direct samples of what's hidden below. Let's break down our home planet. Think of the thin crust as skin, only 1.4% of the planet, composed predominantly of igneous and metamorphic rocks. Beneath that is the thick mantle, by far Earth's largest layer, about 82.5% of the whole volume. Peridotite dominates here, rich in olivine and pyroxene. Further down, the minerals shift. Intense pressure makes them transform into garnet or spinel. And then the core, split into two parts. The outer core is a turbulent liquid sea of iron, nickel, and a hint of oxygen, reaching up to 5,000 degrees Celsius. The innermost core, despite being even hotter, is solid, packed together by pressure so immense that iron can't flow. It's more complex than just crust, mantle, core. Lithosphere, rigid shell, crust plus uppermost mantle. The asthenosphere, it's beneath, hot and plastic. Near melting point, rocks can flow slowly. The deeper mantle is solid but incredibly plastic, deforming at geologic timescales. The D double prime or D layer right above the core is partially melted and mysterious. Then the liquid outer core and solid inner core, metallic and dynamic. Remember, most of what lies beneath us is mantle, a thick, ever-moving engine room. But how do we actually explore what's hidden hundreds or thousands of kilometers down? Through seismology. Seismology is the key, studying how vibrations from earthquakes travel through the planet. Now you must have probably heard of these terms. P waves, S waves. Let's kind of revise it. P waves are primary, push and pull. So push and pull, like a slinky. Fastest and first to arrive. Travel through solids, liquids, even gas. S waves, secondary waves, shake side to side like a flicked rope. Slower, travel only through solids. So you can use a slinky, you'll do this in the lab. Slinky and then a rope, which is for S waves, and slinkies are P waves. Using thousands of seismometers around the globe, we follow how these waves bend, slow down, speed up, and sometimes vanish. For example, S waves can't pass through liquids. When they hit the liquid outer core, they're blocked, creating a shadow zone opposite any big quake. P waves slow and refract, their paths curving as they pass from crust to mantle to core. This is how geophysicists discovered the Earth's layers. The MOHO crust-mantle boundary is marked by a sudden speed jump identified by Andreja Mohorovic in 1909. With advanced techniques like seismic tomography, we can now X-ray parts on the planet, revealing subducting slabs, rising plumes, and shifting zones. The deeper you go, the hotter it gets, but the heat doesn't climb at a steady rate. In the upper lithosphere, temperatures soar quickly, 15 to 30 degrees Celsius per kilometer. Around 100 kilometers down, you're passing 1400 degrees Celsius. In most of the mantle, the temperature gradient flattens, a sign of convection mixing up the heat. The base of the mantle reaches around 3500 degrees Celsius and the core sits near a scorching 5000 degrees Celsius. Why, you may ask? About half of Earth's internal heat is ancient, left from its formative collisions and core formation. The other half is from radioactive decay, uranium, potassium, and thorium breaking down, releasing heat. Mantle convection works like soup on a stove. As heat rises, material expands and moves up. Cooler rock cycles down. That's how, a tea or a stove or any soup or liquid gets heated, right? Heated one in the bottom, that will become less dense, it will go up, and then the higher, the more denser liquid will come down, and overall this whole convection will warm up a soup or a water or a tea. Similarly, in the mantle, there's convection happening. Solid as it is, the mantle still behaves like a slow flowing fluid, moving continents with patient power. On smaller planets that ran out of deep heat like Mars, convection stopped long ago. The interiors are chilling and static. So no convection, that means it's cold, right? All this heat powers another wonder, the magnetic field. Liquid iron in the outer core moves in convection currents, generating Earth's mighty magnetic shield. If you use a compass, you're experiencing it, a slow swirl of invisible lines looping from pole to pole, the magnetic flux lines. But the field doesn't stay constant. Every so often it reverses. North becomes south and back again. These flips have happened hundreds of times, sometimes in just a few thousand years, sometimes spanning tens of millions. When molten lava cools, iron minerals record the direction of the field, offering us a barcode of our planet's geomagnetic history. During a reversal, magnetic field lines twist and distort until the north and south poles trade places. Scientists even model this process using supercomputers, simulating thousands of years in a virtual Earth core. Here's something practical you can see above ground. Isostasy. Imagine a raft floating in thick peanut butter. If you pile mountains that's weight on that raft, it sinks deeper. Erode the mountain away or melt thick ice sheets, the raft floats higher. That's how the crust interacts with the mantle. It's less dense, so it floats, but not on water, on a stiff plastic mantle. After the last ice age, places like the Hudson Bay and Scandinavia have been rising slowly, rebounding as their former load of ice melted away. The process is slow but steady. Oceanic crust being heavier sinks lower on continental crust, a balance sheet written in rock. So what does the ground beneath your feet really hold? Let's wrap up the big ideas one more time. We studied about seismology, remember? P waves, compression, push and pull like a slinky. S waves, shear, they travel like a rope to the planet. P waves can pass through solid, S waves can't. By tracking how these waves move, we uncover the nature and temperature of Earth's various layers. Then temperature. Earth's temperatures climb with depth, steeply in the crust, more gradually in the mantle. These gradients reflect composition and convection. The hottest zones power planetary processes and movement. The magnetic field. Earth's outer core convection generates a magnetic field. Direction of force differ by latitude, and the field flips many times through history, leaving barcodes in rocks. Isostasy, mantle plasticity, means the crust floats. When it gets heavier, mountains, ice sheets, it sinks. When weights are removed, it rises. Oceanic crust, being denser, floats lower than continents. So next time you feel a tremor, see a compass needle swing north or stand atop a hill, remember, it's all connected to the churning, shifting, living interior of our planet. Everything we've covered today lays the groundwork for understanding plate tectonics, which we'll be studying in the next chapter, and why our planet is ever changing. Thank you so much for joining, and please take your assignments, do your study questions. You have been doing great so far. You've been coming for my office hours. If you still have questions, send me an email, and I'll see you in the next one.